Hello and welcome back to Calculus Videos. Today we're going to talk about something called L'Hôpital's rule. This is pronounced L'Hôpital. Any of you who take French, I've heard that it probably means the hospital. You will not be going to the hospital because of this, except, maybe till we get to the last page. But up until then, L'Hôpital's rule is actually a really easy rule to use, so we're just going to jump right in and get to it. L'Hôpital's rule is actually a rule for limits. And we haven't seen limits in a while, so let's kind of backtrack here. L'Hôpital's rule is a rule for limits, and it's actually a rule for when you get a limit that equals 0 over 0. Now, if I kind of backtrack here for a second, we used to do limits where if we had like the limit as x approaches 3 for x minus 3 over x squared minus 9, one of the things I always tell you to do is if you're going to evaluate a limit, first thing I want you to do is plug the number in to see if maybe it works out. But if we plug 3 in, I get 3 minus 3 over 9 minus 9, which is 0 over 0. Well, that's not the answer. That's not the answer to the limit at all. In order to evaluate a limit like this, what we do is we take the limit as x approaches 3 of x minus 3 over the factored form of x minus 9, x squared minus 9. We cancel out the x minus 3's, and the limit of the original function is the same as the limit of the simplified version of the function, which is going to be 1/6. Now this 0 over 0, basically what happens is this 0 over 0 isn't the answer. It kind of gives us the idea that, hey, we got a 0 on top and a 0 on the bottom, which means that maybe there's some way for us to cancel things out. So that's kind of where we're headed. Well, with L'Hôpital, the idea behind L'Hôpital isn't that something cancels out, it's that basically we can simplify it in a different way. So case 1 is if you get a limit that goes to 0 over 0. So if f of a equals g of a equals 0, and f prime of a and g prime of a exist, then the limit as x approaches a of f over g is equal to the limit as x approaches a of f prime over g prime. Okay, what does this all mean? I've got this nice little AKA down here. In other words, if you have a limit that goes to 0 over 0, if the original limit when you plug in the value approaches 0 over 0, then in order to evaluate, what you can do is take the derivative of the bottom, the derivative of the top separately. This is not a quotient rule. This is just there's something on top, take its derivative. There's something on the bottom, take its derivative. Then you evaluate the limit using the new fraction created. If by chance your new limit still results in 0 over 0, you can do L'Hôpital again until you don't get 0 over 0 anymore. So let's look at number 1 here. The limit as x approaches 0 of sine 3x over 4x. So if I go and I plug in 0, I would get 0 over 0. This is a L'Hôpital. So as soon as I see this, I'm going to say, hey, I can do L'Hôpital. So I'm going to come back over here and say the limit as x approaches 0 of sine 3x over 4x is going to have the same value as the limit as x approaches 0 of the derivative of sine 3x, which would be 3 cosine 3x, over the derivative of 4x, which is 4. Now I evaluate this limit. As x goes to 0, this is going to be 3 times the cosine of 0, which is 1, over 4, which is 3/4. So the limit as x approaches 0 of sine 3x over 4x is 3/4. Now you may be saying, wait a minute, that sounds familiar. We did that before. Well, yeah, you did this before where you said, wait a minute, if I have the limit as x approaches 0 of sine ax over bx, it equals a over b. That's still true. This is just another way to get there in case you forgot this little generalization. Okay, long story short, example 1, we got 0 over 0. We took the derivative of the top, the derivative of the bottom, and then reevaluated. So let's do it again here for this next one. The limit as x approaches 0 of 1 minus cosine 2x over 5x. All right, I'm going to plug in 0. I'm going to get 1 minus 1 over 0, which is 0 over 0. So we're going to do L'Hôpital. So the limit as x approaches 0 of this first thing is equal to the limit as x approaches 0 of the derivative of the top and the derivative of the bottom. The derivative of negative cosine 2x is going to be positive 2 sine 2x, and the derivative of 5x is 5. Now when I plug in 0, 2 sine 2x is going to be 2 times 0 over 5, which is 0. And there's your limit. Moving on, same thing going on. So if I have 0 here, I'm going to have the square root of 1 minus 0 over 2 over 0. Well, that's going to be 0 over 0, so I can do L'Hopital. You have to do that first step to make sure you get 0 over 0, or you can't do L'Hopital. So if I take the derivative now, I'm now going to be evaluating the limit as x approaches 0 of 1 half times 1 plus x to the negative 1 half. Minus 1 goes to 0, then minus 1 half. On the bottom, this is going to be 2x. So now I'm going to evaluate this second limit here. I'm just kind of breaking this up here. As x goes to 0, this is 1 half times 1 to the negative 1 half minus 1 half over 0. Hey, that's a 0 over 0. I get to do L'Hopital again. So now I'm going to do the limit as x approaches 0. The derivative of the top is going to be, let's see, negative 1/4, 1 plus x to the negative 3 halves over 2. Now I'm going to plug 0 in again, which is going to give me negative 1/4 times 1 to the negative 3 halves over 2, which is negative 1/4 over 2, which is negative 1/8. And there's your limit. All right, why don't you try example 4 by yourself? Hit pause and then come back. All right, hopefully you're back now. When we go to take this one, first we want to plug in pi over 2. So I have 1 minus 1 over 1 plus the cosine of 2 times pi over 2, which is cosine pi, which is negative 1. So this is going to be 0 over 0. Oh, my pen got confused. 0 over 0. So I can do L'Hopital. So now I'm going to take the limit as x approaches pi over 2 of the derivative of the top, negative cosine x, the derivative of the bottom, negative 2 sine 2x. Now I'm going to plug in pi over 2. Well, I'm kind of anticipating that this is going to be 0 over 0 by looking at it, which it is. This is going to be 0 over 2 sine pi, which is another 0. L'Hopital again. Oh, stop doing that. Limit as x approaches pi over 2. Derivative of the top is going to be positive sine x. Derivative of the bottom is going to be negative 4 cosine 2x. And let's see, when I plug in pi over 2 now, I'm going to have the sine of pi over 2, which is 1, and then negative 4 cosine pi, which is going to be 1 over negative 4 times negative 1, which is 4. 1/4. And there's your answer. All right. Now, moving ahead, the next case of L'Hopital is infinity over infinity. And you're going to notice that this looks very similar to what we had on the first page. What this gets at is if you have f of x and g of x, and they both head toward an infinity, doesn't have to be the same infinity, but they both head toward an infinity, you can do the same exact thing. You can take the derivative of the top, the derivative of the bottom, and reevaluate. So in other words, L'Hopital's rule works for both infinity over infinity and 0 over 0. So if we take a look at example 1 here, the limit as x approaches infinity of 3x squared, blah, 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 blah. All right, the first thing you may notice is you might be saying, wait. I did this in pre-calc. We did this at the beginning of the year. If you say x is going to infinity, you can compare the degree of the numerator and the denominator. So I'm going to do it the old way and then do it the new way. So the old way is, wait, I can just look at the highest powered terms, which is 3x squared and 4x squared, and say, you know what? They have the same degree, so it goes to the ratio of the coefficients. You're absolutely right. That's perfect. We're going to do it the new way now. If I forgot about the old way and said, all right, as x goes to infinity, this is going to be 3 times infinity minus 5 times infinity. This is going to be infinity on top. It's going to be infinity on the bottom. Now I get to use L'Hopital. So I'm going to reevaluate using the limit as x approaches infinity of the derivative of the top over the derivative of the bottom. Plug in the infinity again. Well, if I put infinity on top, I'm going to have infinity over infinity. Do L'Hopital one more time. The limit as x approaches infinity of 6 over 8. Well, the infinity doesn't have to go anywhere. 6 over 8 is just 3/4. Okay? Now, honestly, all things considered, I'd prefer that you know it the old way. If you have a rational function, pardon me, a rational expression, and they both have the same degree and x approaches infinity, you just take the ratio of the coefficients. That's going to be way easier, but I wanted you to show that both ways work. All right, so coming down to this next one, is x approaches pi over 2 from the right of secant x over 1 plus tan x. Okay, well, let's see. If I plug in pi over 2 into secant, that's the same as 1 divided by cosine of pi over 2. And the cosine of pi over 2 is 0. So wait a minute. 1 over 0, what's that? Well, 1 over 0 is going to be infinity as far as limits are concerned, because the cosine of pi over 2 is approaching 0, which means secant has an asymptote. So as x approaches pi over 2 from the right, cosine is going toward positive infinity. I'm sorry, secant is going toward positive infinity because cosine is going toward 0. Same thing for 1 plus tan x. So if I have 1 plus tan x, 1 plus tan pi over 2, well, the tangent of pi over 2 is the sine of pi over 2 over the cosine of pi over 2, which is like 1 over 0. This is going to go to infinity for the same reason. So I have an infinity over infinity kind of day, which means I'm going to do L'Hopital again. The limit as x approaches pi over 2 from the right for the derivative of the top and the derivative of the bottom. Well, the derivative of secant is secant tangent, and the derivative of tangent is secant squared. Anytime you have a limit and you're supposed to evaluate it, feel free to simplify before you evaluate. Simplifying does not affect the value of a limit. So I'm going to cancel out this secant right here with one of the secants from down there. So I have tangent over secant now. And you know what? I kind of want to see, maybe this simplifies more. So I'm going to come down here and say, well, tangent divided by secant is the same as sine over cosine divided by 1 over cosine, which is the same as sine over cosine, forgot my x here, sine over cosine times cosine over 1. Those cancel. This is the same as sine x. So tan x over secant x can be rewritten as just sine x. And the limit as x approaches pi over 2 of sine x is 1. Now, had you not simplified that, we would have had to do L'Hopital again, but I, again, really want to emphasize to you that if you have a limit that can be simplified before evaluating, you should absolutely do so. It's going to make your life a lot easier. All right, if you want, hit pause, try the next two on your own, and then come back. All right, maybe you hit pause, maybe you didn't, but here it is. So, let's see. We have the limit as x approaches 0 of ln x over cotan x. Well, ln x has an asymptote as x goes to 0, so as x comes at 0 from the right for ln x, that's going to head toward negative infinity. Cotan as x goes to 0 also has an asymptote. This is going to positive infinity. So I have two infinities. So this is going to be a L'Hopital kind of thing. I'm going to take the derivative of the top and the derivative of the bottom. So 0 from the right, the derivative of ln x is 1 over x. The derivative of cotan x is going to be negative cosecant squared x. And I don't really like the way that looks, so I'm going to rewrite it before I even evaluate it. I'm going to rewrite this, well, 1 over x means that x can go on the bottom, and dividing by cosecant is the same as multiplying by sine. So as x approaches 0 for sine squared x over x, I'm going to end up with 0 over 0. Hey, that's another L'Hopital. So I'm going to take the derivative of the top and the bottom again. The derivative of sine squared is negative 2 sine x cosine x. And the derivative of x is 1. As x goes to 0, this is going to be negative 2 times 0 times 1, which is 0. There's your limit. And then last but not least, we have x goes to 0 of this guy right here. Okay, fine. So ln of that over ln of that. Well, as x goes to 0, my numerator is going to be the ln of 0, which I can't really take. But again, this isn't really 0. It's close to 0. So this is going to be negative infinity. That's going to be negative infinity. This is a L'Hopital kind of thing. The limit as x approaches 0 from the right for the derivative of the top, which is going to be 2x plus 2 over x squared plus 2x. On the bottom, this is going to be 1 over x. I'm going to simplify here. So 2x plus 2 over x squared plus 2x times 1 over x. This is going to be x approaches 0 from the right of 2 times x plus 1 over, let's see, x times x plus 2. I'm factoring to see if my life might get easier. And this 1 over x on the bottom really pulls an x up on top here. So these x's are going to cancel. And so if I take the limit as x approaches 0 of the remaining stuff, I'm going to have 2 times 1 over 0 plus 2, which is 2 over 2, which is 1. And there's my limit. All right, I'm going to stop here. There are 2 more cases to come, but I am going to put those in the next session. So there's L'Hopital. Long story short for L'Hopital so far is that if you have 0 over 0 or infinity over infinity in a limit, you can take the derivative of the top over the derivative of the bottom, find the new limit, plug it in, call it a day, and evaluate. All right, I will see you back for case 3 and case 4 of L'Hopital's rule.